In the binary representation of numbers, bitwise operators act upon individual bits. We will soon understand what this means. But for now, let's take a brief look on binary representations. So you know that any decimal number, for example, let's say 4, can be represented in binary like this. So if you don't have any idea how to convert this, you may look up this thing before continuing in the video. So these bitwise operators would act upon these individual bits of numbers. So there are various types of bitwise operators. The first one is NOT. So NOT bitwise operator flips each bit of the number. For example, if you have 4 in its binary representation, it would become, after applying the NOT operation, it would become like this. But in C++, we use 2's complement, and the integers, the int data type that you use, uses 32 bits to represent numbers, and they are represented using 2's complement. So if you don't know what a 2's complement is, go and look that up first. So if you have int some integer whose value is 4 and you print its not a, then you will print the number whose binary representation, whose 2's complement binary representation is like this. So they are going to be ones, and then this one is going to be flipped to a 0. Then you will have, so these are 32 bits. This bit is for the sign. If it's 1, the number is negative. If it's 0, the number is positive. So as we can see, this is going to be some negative integer. So if you convert it into decimal, considering that it is represented in 2's complement form, you will get its value. But since this is not the topic we are covering right now, so I will leave it here for now. So here it's just clear that plus 4, which was a, was like this, many zeros, and so this was 32 bits. So this was plus 4, and now after applying the after applying the NOT operation, each bit got flipped, 0 became 1, and this 1 became 0, this became 1, this became 1, and we got this number. Okay, now let's look at the second bitwise operator, which is AND operator. So AND operator is denoted using this symbol. NOT was a unary operator. That means we only needed a single number to apply it upon. But AND is a binary operator. We need 2 numbers to apply it upon. So suppose you have the first number as 4 and second number as, let's say, 7. So if you convert it into binary, it would look something like this: many zeros and 4. Again, many zeros. So this. Now what the bitwise AND does is, think of it like this: if both bits are 0, it would result in bit which is 0. If both bits are 1, it would result in a bit that is 1. If one of the bits is 1, it would still result in 0. So you can think of it like this. You ask, you need 50 rupees. So you need 50 rupees, and you ask two of your friends, friend A and friend B. You are C, you have friends A and B, and you ask two of your friends to lend you 25 rupees. Now, when is your need going to be fulfilled? When both of them lend you 25 rupees. So if none of them gives you rupees, your need is not going to get fulfilled. 0 means need not fulfilled. 1 means your need is fulfilled. So if only one of them gives, still you will need 25 rupees more. So still your need is not going to get fulfilled. But if both of them gives, A gives and B gives, then your need is going to get fulfilled. So this is an analogy or an example for bitwise AND. So here we had these two numbers. Now they're bitwise AND. So this would be A and B, bitwise AND. Just see this, 0 and 1. Just one of them is 1. You put a 0 here. Again, corresponding bits, you put the 0 again. Again check the corresponding bits. Both are 1. When both give, our need is satisfied and we can put 1. So I guess this was simple enough. Now let's look at bitwise OR. So in this case, think of it as, first I will draw the input-output table. This is bit of A, this is some bit or corresponding bit of B, and this is going to be our corresponding bit of A or B. Okay, so if both are 0, then it's 0, otherwise it's 1 in all other cases. So now let's look at the analogy really quickly. So here you directly ask for 50 rupees. So you ask both of your friends A and B. Let's see here. You ask both of your friends, you need 50 rupees, and you ask for 50 rupees. Now you can see, if both of them denies to give you 50 rupees, your need won't be fulfilled. Okay, so that's why here we have 0. Even if one of them gives you 50 rupees, you only needed 50 rupees. So even if one of them gives you 50 rupees, your need would be satisfied. So we have 1 here. Now if both of them gives you 50 rupees, you have more than enough. So your need is again satisfied. So we have a 1 here. Okay, so let's take a decimal example. Again, we can take the similar example. Let's say A and B. So let's take this one as 4 and B as 1. So 4 would be 100 and B would be 001. Now if we calculate A or B, this is a bar symbol used to represent OR. So here one of them have 1, so 1, 0, 5. This is the binary of 5. In C++ we use this symbol to apply XOR operation. Okay, so let's first draw the same kind of table. This is some bit of the first number, this is some bit of the second number, and this is the resultant bit when we take the XOR. Okay, so these are the four possible cases for the corresponding bits. Remember, we apply the operations on the corresponding bits to get a resultant bit. So these are those corresponding bits. So in this case of XOR, it is something like this. To take an example, so the example would be something like this. Let's say you have a bucket. Let's say you have a bucket and you have two more buckets. Okay, let's say this is bucket C, this is bucket A, this is bucket B. Now these two buckets are full. Okay, and they all have equal capacity, like each has same volume. Now you want to fill the bucket C using these buckets, but you want to fill it, but you don't want to overflow it. So just to take an very simple analogy, you don't want to overflow it, you just want to fill it. So now these are the two conditions for this simple scenario. So in this case, you see, if you use a bucket A, if you pour the bucket A, then A would be A's bit would be 1, and if you pour the bucket B into C, B's bit would be 1. If you pour the water of B into C, B's bit would be 1. So let's look at this. If you don't pour A and you also don't pour B, then C would remain empty. So this condition won't be satisfied. So our goal is not achieved, so we put a 0 here. 1 means goal achieved. So this was our goal. Okay. Now, if you don't pour the water of A into C, if you don't pour the water of A into C, but you pour the water of B into C, then we fill it, we fill the bucket and we don't overflow it also. So our goal is achieved. In this case also our goal is achieved. But if you pour the water of A into C and then you pour the water of B into C, then the bucket will overflow. So if the bucket overflows, our goal is not achieved. That's why we put a 0 here. So in such scenarios, we can think of it as using an XOR maybe, or some other scenario. It depends. Okay, so now let's take a numerical example here. So again we can take 4 and 7. This was 4, this was 7, and this result would be 4 4 XOR 7. So one of them is 1. So that means we need to put a 1. One of them is 1. We need to put a 1. Both are 1. We need to put a 0. So we got this result, and this is 3. So here I am writing 3 directly because the prefix bits are not affected, because 0 XOR 0 would be 0. So there would be just zeros. But in the case of not operator, the if I flip this, the preceding zeros would get flipped to 1. So that would change lots of things. So you must learn about 2's complement, and you would get some number like this. And then you need to convert it back into decimal by considering it as a 2's complement representation of that decimal. Okay, that's a topic for some other time. Let's look at 2 more bitwise operators. Now the left shift operator shifts each bit to left, and this one shifts to right. And what happens at the end points? Well, if it's a left shift operator, then we put a 0 on right side. And if it's a right shift, we put a 0 on left side. If it was a left shift operator, we would discard left side bits, and if it was a right shift operator, we would discard the right side bits. Now let's take a quick example of this. So first we take the example of left shift operator. So here we put the number, and here we put how many times we are performing the operation. So suppose we have 4 here, and we do this 3. This means do the left shift 3 times. So this would, and we in the left shift we add 0 on the right. So assuming this was a 32-bit number, not 3 bits, so there will be zeros here. Okay, so this would result in, since we are doing it 3 times, 3 zeros will be added. Okay, so this will become this. Now that was pretty simple. Now what if we had a 1 here at the end? So this is some other number. Okay, so and then we do it, let's say even 1 times, just 1 times, then this 1 would get discarded. This 31st number from this 31st bit from the right side would become the 32nd bit, because this one got discarded, and each bit got shifted towards the left. Okay, and 1 extra 0 will be added here. Okay, so discarding this bit and adding a 0 here just has the same effect as shifting everything to the left. Okay. Now, interesting thing to consider here is when we add a 0 to a binary number, what happens? So we add a 0. So see this. So earlier this was 2 to the power 0, to the power 1, to the power 2. Okay. And then we add these to get its value. Okay. If we add a 0 at the end, each power increments by 1. So this was representing what? So whatever the bit was here, 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. After adding a 0 here, now each power got increased by 1. How? See, now this 2 to the power 2 is now 2 to the power 3. Because now this is the 2 to the power 3. Okay. So each power got increased by 1. That is same as saying if I had multiplied this by 2, these 2's get multiplied by this and it will increase the power by 1. And of course, since we are adding 0 at the end, here it would be 0 into 2 to the power 0 at the last. So it would become 2 to the power 3 plus 0 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. So this 0 is the one we added. So even if let's say this bit was 1, okay. So suppose this was like this 5. So this bit was 1. Okay. We added a 0 at the end. Okay. So this got multiplied. So each power got increased by 1. So when we shifted, each power got increased by 1. Okay. So that is same as taking this and multiplying it by 2. As you can see, we multiplied it by 2, we got this, which is same as this. Okay. I took 1 here, so just to explain you, okay, that shifting left side has an equivalent effect as multiplying the number by 2. And if you again shift it, then it would be multiplying it by 2 again. So if you shift a number, k times, it is same as multiplying that number by 2 to the power k. Okay. And for the right shift operator, it's just same almost same as left side. It's just that we shift this side instead of shifting that side, and we will be discarding the rightmost bit, so that would have same effect as dividing by 2 to the power k. If we shift it k times, it is having the same effect as dividing by 2 to the power k. For example, and actually that might result in a floating point number, so we discard the point, we just take the floor. Okay. For example, if we had 5 here, we add a 0, it becomes 10. So this was 5, we added a 0, became 10. Why? Because earlier this one was here representing to the power 2. This was to the power 1. This was to the power 0. Now by multiplying by 2, by adding a 0, each power got increased by 1, which is same as multiplying them by 2. Multiplying this sum by 2, each power would increase by 1. That's fine. I hope this concept is clear. And if you, again, if you just remove the last bit, this will again become 5, which is 10 by 2. Suppose it was 11, if it was 11, and if you remove the last bit, so you have the 5 now. So 11 by 2 is actually 5.5, but you discard this 0.5, okay? Why? Because we discarded a 1, right? We discarded a 1 here. Here we were discarding 0. Here we discarded a 1. So we discard the 0.5 also. And we are left with this. So for these odd numbers, we can take the floor value. So I hope this concept is clear.